let me just make sure I may have the chat here. Oops, this is good. Okay, so I can notice the chat. Okay, so today we are going to talk about spatial analysis. And so here we have mainly we have 5 points. Well, I guess I do not need this one. Okay, we have 5 points. So first, I would like to talk about correlation and how to calculate the correlation, because correlation will be helpful for spatial analysis. And then we are going to talk about how can correlation be applied in spatial analysis. So I will use the 1D spatial data as an example, and I will briefly talk about 2D spatial correlations. And then I also want to introduce another concept, which is covariance. So correlation and covariance, they are a couple. And I will also introduce variogram. And then we are going to talk about how to interpolate spatial data. So we generally have 2 methods, deterministic methods and statistical methods. And then we are also going to talk more about statistical methods. So during this class, we can see we have several calculations, but we only need to care about the first one. So for the correlation calculation, we will have this homework assignments, and it will be asked in the quiz. But for the calculations, in the rest of them, you guys don't need to do the calculation. I will show some of the equations to just enhance our understanding, but we are not going to do the calculations for this. Okay, so first, let's look at variance. I think we are very familiar with variance, and here is the definition. And we know that variance is a measure of dispersion. But here, note that this is the population variance. We know that in the statistics, we have the variance, like sample variance, which is n-1. And we have blah, blah, something here. So for the population variance, we use n. For sample variance, we use n-1. So population variance is a parameter, but for sample variance, this is a statistic, because we are going to use the sample variance to estimate population variance. So I just want you guys notice the small difference here. And in this definition, actually we can use some other notations, like we use this variance of x to represent the variance. And we use the expectation of x to represent mu. We just change the symbol because it will be easier to derive some other stuffs. So we can rewrite this equation into here. So basically, we just replace sigma square with variance of x and replace mu with expectation of x. And so we can see that it means that the variance of x is the average of this part, because it is divided by n. So it is the average of this whole part. And in other words, the variance can be rewritten into this one, because this is the average, and we know the mathematical expectation refers to the average. So we just add the mathematical expectation notation here to represent the average of this part. So these parts are equivalent. And then we can do some transformation, like we can open the bracket based on the properties of expectation. And finally, we can get this relation. For this relation, we can see that so variance of x is the expectation of x times x, and the minus expectation of x times the expectation of x. So we have double x here, double expectation of x here. But we know that this is a variance, and this is a like weird shape. But we can use this to define covariance. So covariance is a measure of how much two random variables vary together. And I can consider it as like the friendship. Like we can see, let's just see the definition. So for covariance, which we have two variables, x and y. So we just replace one x as y. So for the variance, we have double x and a double expectation of x. But for covariance, we just replace one x to y and the expectation of x as expectation of y. So basically, we can see that variance is a special case of covariance. So basically, we have two people here, and the variance is a measure of itself, like me and myself, the friendship between me and myself. But for the covariance, we are measure the friendship between two different people here. And based on this definition, we can just rewrite, open the expectation, and we can finally have this expression. So this expression is also a little bit complicated. And so what can this tell us? So basically, it tells us that, as I mentioned before, covariance is a measure of how much two random variables vary together. And on the left side, we have some examples. For example, this one, the covariance equals 2, and the covariance equals to 4.5. We can see from the data, like they are positively correlated. And this one, compared with this one, like they are more correlated than the rest. On the other hand, if we have covariance equals to 0, it means that they are mainly unrelated. And we can also have the negative covariance, which means the x and y, they are negatively correlated. And we can see if we have a larger number of covariance, it means they are better correlated. We can calculate covariance. As I mentioned before, we have this a little bit complicated expression, but we have already done the linear regression calculations. So this is like similar to that. So basically, suppose we have two sets of data x and y, and note that they are paired. So this is 1, 2, 3, 4, 5. And we have two sets of data, and we can also follow the different steps. So for the first step, we can calculate the average of x and the average of y. Like we can do this in the Excel table. So we can have average of x and the average of y. Next, we can calculate the difference between every x minus the mean of x. So we can do something like this. We use the x minus the average of x. So we can get this value. And similarly, we have the y here. And then we can calculate the product of these differences. So here shows the product of these differences. And lastly, we can calculate the average of this product here. So this is the covariance. So you guys may use Excel to reconstruct this table by yourself. So you guys can have understanding on this calculation. So far, do you guys have any questions? No? Do you guys? No, okay. So that's okay. Let's look at another parameter, that is correlation coefficients. I think this is more familiar, like you guys are more familiar with this one. So because covariance can be infinitely large or small, and it depends in the magnitude of the data. So it is hard to make a standard, or it is hard to compare data from different places, or for cross comparison. We can introduce correlation coefficient as a normalized covariance. And the correlation coefficient is defined as the covariance divided by the variance of x times the variance of y, and then we make the square root. So in other words, it equals to the covariance of x, y divided by the standard deviation of x times the standard deviation of y. So if we have the data and we know how to calculate the covariance, and we also know how to calculate the standard deviation of x and y, and then the correlation coefficient can be calculated by us by hand. And here are some mathematical derivation, and finally we can get this one. So we can use this expression to do the calculation. So this is method number 1. On the other hand, we may avoid calculating covariance, and we can use this equation to do the calculation. And this is also this also looks a little bit complicated, but we have already done the linear regression calculation. Similarly, we can define the mean x and mean y, and sxx, syy, and sxy. So they are the same in linear regression. And if we define like this, the correlation coefficient can also be calculated based on this expression. So this is much clean. And because we know how to calculate sxx and syy, so we know we can calculate the R, the correlation coefficient. And here shows the example. So here the definition, and here are the definitions of Sx, Syy, and Sxy. Again, we have the same data set, and we have several steps. So basically, first we can calculate the average of x and y, and then we can calculate the difference between x and the mean of x, and take the square. So we can have Sxx. And then we can do the same to y data. And then we can have Syy. Finally, we do the cross product. We can have Sxy. By having all of these 3 values, we can just plug them in the equation. We can get that the correlation coefficient of this data are 0.94. So far, do you guys have any questions? Good. So again, I recommend you guys to reconstruct this Excel table so you can have more, you can get more familiar with the calculations. Let's look at some properties of correlation coefficient. So from the definition of xxx, syy, we know that the product of these two is greater or equals to sxy. So if we have these properties, we can say that the correlation coefficient is has this range, like it is greater than -1, but smaller than 1. And intuitively, we know that if it is equals to -1, it means that the x and y data, they are perfectly negatively correlated. And if it is equals to 1, it means that they are perfectly positively correlated. And if it is equals to 0, it means that x and y, they are uncorrelated. But in practice, we may have some correlation coefficients of different values between 0 and between -1 and +1. So in this case, sometimes we can use the descriptive statement to describe the strength of their correlation. Like we can say they are we have some classifications. And again, this is similar to the scale of the water hardness. So we may, like different people may have different classification methods. So it would be better to specify or keep consistent, like which standard you are using. But in practice, it is good to report both R values and the description. So we can see X and Y, they are highly positively correlated. And we can have a bracket and say R equals to like this one. So this will be the most accurate way to describe the correlation. So far, do you guys have any questions? No? Okay. And the next one is, like, when I was young, I always have this question, like, we know that in the linear square, we have the R square, which is called coefficient of determination. And we also have the correlation coefficient. So I was thinking, what's the relation between these two? And after some studies, I find that, so basically, the correlation coefficient R equals to the square root of coefficient of determination. And on the right side is an example, intuitive example. Again, we have the same data here, like X and Y. So they looks like this. And this is a scattered plot of X and Y. We can, after our previous calculation, we know that R equals to this value. And we can use the Excel to automatically calculate R squared for us. And it equals to this value. So we want to compare if they are equal. We just take the square root of this R squared. And we can say it equals to this one. So they seems to be equal. Like during practice, we may have some small differences because of the decimal accuracy of your calculator, but they are theoretically equal to each other. Also, we also have some correlation coefficients, like the correlation between R and B. So we know B refers to the slope. And we can see that R and B, they are kind of like positively correlated. And the coefficient is this value. So it's also like it depends on our data. So far, do you guys have any questions? Good. Okay. And then by knowing the correlation coefficients, so far you guys need to know the method to calculate correlation coefficients. But after that, like from now on, you guys don't have to worry about the calculations. I will not ask the calculation questions from this slide to the end. And so here I'm going to introduce like how can correlation apply in spatial analysis. At the very beginning, I want to talk about 1D data because this is relatively intuitive. So suppose we measure PM 2.5 concentration from 4 sites, like 1, 2, 3, 4, like at different places. And these are our results. So basically, we have like the 0, like, and then we just holding the sampler like from 0 to like 20 meters. And then we can get, like this is the concentration of PM 2.5, and this is the distance from this 0. And for each one, we have like 20 meters. And this is site 1, site 2, site 3, and site 4. So do you guys find any special pattern or characteristics of each site? Yes?
So concentration decreases at site 1 as you move farther away.
Mm-hmm. How about you?
For site going inwards, concentration increases.
Increases, yes. How about you? You want to? What's the characteristics you notice of site 2?
For site 2, it looks like it's almost cyclical.
Cyclical?
Yeah, as you
Yes.
move away, the concentration is fluctuating.
Yes.
But I don't really know what that, like, for site 1, like, you're moving away from, like, if it's the concentration of a pollutant, like, you're moving away from the site where it's filled. At site 4, you're moving towards the site where it's filled. I don't know what's going on at site 2.
I feel like it's a steady concentration, like based on how far away you go, but it's like it comes in waves. So
This
like
one.
this thing.
Yeah, or maybe, like, if it's pollutant, like, it was spilled at different
Oh yeah.
intervals, like, there were multiple
Yeah.
spills, and you're seeing the effects of it.
Yeah.
Yeah, oscillating. Yeah, it's kind of like that. So it has some circulation, or it has some periodic change, like up and down, up and down, up and down. And how about site 3?
Stays constant.
Yeah, like relatively constant. It has some small fluctuations, but in general, it is relatively constant. And yeah, site 2 is oscillating. Yeah. So, like we already know the characteristics of these 4 sites, and they are like the typical examples. So, let's look at the first site in details. So, for the first site, we may have some questions. Like, so this is the shape of first site. We know that it is constantly decreasing, like as we go far away from the first site. We may have a bunch of questions. So, what is the correlation coefficient between CD and CD? So, we can consider the 0 meter and the concentration of 0 meter. And again, what's the R between CD and CD plus 1? It's like, so for this one, we have 0 meter, 0 meter, and 1 meter, 1 meter. So blah, blah. So for this one, we have C like 0 meter, vs C 1 meter, and C 1 meter versus C 2 meter. So something like that. So again, we can ask like what's 2 meter? We have 4 meter, all the way maybe to 10 meter. And this distance, we call this lag distance, or delta D. So this delta D can be like 1, 2, blah, blah, to 20, because we have like the far away points, they are 20 meters. So to answer this question, we can do the calculation. And the calculation is a little bit long. And we can see if we want to answer the first question, so where the delta D equals to 0. So actually, we are calculating the correlation between when CD equals to 1, equals to 0, and itself, and C1 at 1 meter and itself, and again all the way up. On the other hand, if delta D equals to 1, so basically this is the D equals to 0, and this is D equals to 1. And this is 1, 2, 2, 3, blah, blah, blah. And we can see we don't have a data here. And again, we can have delta D equals to 2, delta D equals to 3, and all the way delta D equals to 20. And so do you guys have questions about this? And then we can do the calculation about correlation coefficient of each one. Oh, and here I want to introduce a concept that is called autocorrelation function. So autocorrelation is known as a serial correlation. It's the correlation of a signal, and our concentration can be considered as a signal with a delayed copy of itself as a function of delay. So the delay here is a delta D here, and the signal refers to the concentration. And this is the more accurate definition, but you guys don't have to remember it. And here is an example. We have a signal here, and then we can calculate its autocorrelation here. Like we have different delays, like we have different Ds here. So let's look at the autocorrelation of site 1. We can see the site 1 is decreasing. And if delta D equals to 0, because the correlation between me and myself is always 1. So when delta D equals to 0, r equals to 1. But as d increase 1, 2, 3, 4, 5, we can calculate all of these r's, and we can see they are relatively large, like they are all above 0.9. And we can also make the autocorrelation function plot. So this is delta d, and this is r. I just plot up to 10. And we can see for the sites that the concentration is consistently decreasing, the autocorrelation is kind of like stable at a relatively high level. And then what's it look like for site 2? We can see that intuitively the site 2 is kind of oscillating or periodic change. We can say again, when d equals to 1, it is 1. But when as d increase, we can see the shape is like a circle, and then another circle. It's kind of like this. So it has some pattern, and we can plot the autocorrelations R versus delta D. And we can see that it also has some spatial pattern, which means the characteristics of site 2 can be reflected by the autocorrelation function. Now let's look at site 3. For site 3, it is kind of like stable with some small fluctuations. And again, when d equals to 1, that equals to 0, this is 1. And then we can calculate r at different delta d. And we can summarize it here. So in general, we can say that when delta d equals to 0, it is 1. But when delta d increase, we can see that the correlation coefficients, they are relatively small at a low level. So this is the autocorrelation function of site 3. And let's look at the last one. So for the last one, it is consistently increasing. And we can see, again, we can have this autocorrelation plot. But interestingly, we can find that the autocorrelation stays at a relatively high level. So this is the same for the first site. So if we put them together, we can find that at some extent, the autocorrelation function can reflect the characteristics of the site. And in the real situation, we know that the data will not be this specific like this particular. So they are just the special case of our real life. So in our real life, it will be the combinations of these stuffs. And let's just look at this plot again. Like by looking at these figures, like we can tell by our eye they have some characteristics. But for more complicated cases, like this one, it is very hard to tell what's the characteristics of this plot by our eye. But we can use the autocorrelation function. We can see it looks like this. So we can see this is gradually decreasing. On the other hand, it also has some oscillating. So it can reflect some information of our sample data. And here is a take-home message. So spatial characteristics can be reflected by autocorrelation function, especially when the cases become complicated. So far, do you guys have any questions? No? Okay. So now let's look at the 2D cases. For 1D or for 2D, because we also, like if I'm here, for 1D, I want to know like 1 meter from me, because for 1D, we only have one direction. So I can find two data, like which is 1 meter away from me. But if I'm on a 2D map, and then all of the data in this circle with a radian equals to 1 meter, they are all 1 meter away from me. So when we are doing the 2D data, we need to consider all of these data points in the circle. So the computational intensity increases significantly. So we do not have to do this calculation, but for 2D data, we need to find the pairs of given distance, like say like this, but from all of the directions. And then we can use this data to calculate the correlation coefficient. So the calculations are the same, but the amount of calculation increases a lot. And here, I just want to intuitively introduce the correlation function and the covariance function, because they are frequently used in like 2D spatial statistic analysis. Again, you guys don't have to remember these definitions. So I just want to intuitively like introduce these two. So for 2D spatial analysis, we do not usually use correlation versus lag distance, but we use the variance versus lag distance. So this is their transition, but they are kind of equivalent. So intuitively, we can see that like this is a lag distance, and the y-axis refers to the correlation. Intuitively, we know that the correlation decreases with the lag distance. It means that if we are very close to each other, our concentration is more likely to be the same. But if you are very far away from me, then the concentration between us may have no correlation. So the correlation will be very low until it gets to 0. So the correlation function which is defined as this. So the plots will be something like this. And then we have a here. It means when h is greater than a, it means we have no correlation. We are kind of independent. So similarly, we can define the covariance function. So covariance function is just like we use a constant minus this curve, and then we will get this curve. So for correlation function, it decreases with distance. But for covariance function, the covariance increases with distance. And this is the only difference. And for covariance function, intuitively, we can consider it as the variance increases with distance. Like if we are very close to each other, the values between us are very similar. So the variance is relatively small. But if you are very far away from me, then your possibility of having other values increases. So the variance increases. But traditionally, in 2D spatial data analysis, they will use this one, which equals to 1/2 of this variance. And they call that variogram or semi-variogram. So basically, when they have this variance, they just divide it by 2. This is just their transition. So far, do you guys have any questions? No? And then here are some examples. We can see that environmental data are usually spatial correlated at some distances. And I showed this data in the alkalinity lecture. So this is the surface alkalinity in the ocean. We can see that if I'm standing here, and we can see around me, the alkalinity are relatively high. So like if it is near me. Similarly, if I'm standing here at very low alkalinity, and the alkalinity around me, they are also supposed to be low for a relatively short distance. But if I evaluate the distance far away from me, we can see that if at this distance, we have some high alkalinity, we also have some low alkalinity, or have some medium alkalinity. We can see that the variance increases because I can have many different kind of possibilities. So in this case, we can see that the correlation decreases, but the covariance increases as distance become large. And this is the same for the surface pH change. We can see they are also spatially correlated at some distance. And in practice, we have we know that the covariance increases with distance. And when we have the empirical data, we can use some models to fit that data. And here shows some of the models. So basically, we have these three models are the common models used in environmental science. But we still have some other models, like this one reflects the oscillation, and also we have some other situations. And then I'm going to talk about how to interpolate spatial data. And we have talked about the spatial correlation, so we can use the statistic ways to do the interpolation. And this statistical method is called Kriging. So Kriging is based on spatial correlation, but we still have some deterministic methods. I think maybe you guys have already seen them in previous semesters. Mainly we have three deterministic methods, like inverse distance method, weighted methods, natural neighbor interpolation method, and spline method. And so, for example, we have, in practice, we may have the CO2 concentration monitored at different weather stations. But we want to know the concentration of CO2 in the whole area. So in this case, we can do the spatial interpolation. And actually, for our weathering data, most of them are spatially interpolated. And here is a nearest neighbor interpolation method. So basically, the algorithm is straightforward. So we have different points, say these 2 points, and then we just make the line, and then we find the middle of this line. And again, we find the middle of this line. So we just find the middle of each line between 2 points, and then we can make the polygon. And we can assume the concentration within one polygon equals to the concentration of this single point. And here we just remove the boundary lines, so they look like this. We have some advantages and disadvantages of this nearest neighbor interpolation method. So it is computationally cheap, and it has ability to preserve original values in the unaltered sense, because we did not change the concentration of our original measurement. But it also has some disadvantages, like it has noticeable position errors. For example, if I'm interested in the concentration here, we can see that empirically we know that the concentration could not equals to this one or this one. It should have something in between, but it cannot reflect this sense. And again, it is a non-smooth interpolation method. And so for this one, do you guys have any questions? No? And the next one is an inverse distance weighted method. So this method assumes that the variable being mapped decreases in influence with distance, and from its sample location. So it is pretty similar to the idea of spatial correlation. Like if we are interested in the concentration of this place, and then it can be calculated by different contributions from other points, and the weight, and we can assign a weight to here. So each one has a weight, and this weight is a function of distance. So basically, this refers to the distance between the interested point and any point of xi. So the weight just equals to the distance divided by 1. And we also have a p here. P is a parameter, and it's usually equals to 2. So we have something like this. So once we have the distance between 2 points, we can just plug this number in, and then we can have the weight of each point. And then we just calculate the weighted average to estimate our concentration. And here shows an example. So we use the same data set to do the spatial interpolation. We can see that in this case, p equals to 1/4, and p equals to 2, and p equals to 16. We can see that as we select different p values, the results are different. So here may comes to another question. How can I determine the p value? Like we know commonly p equals to 2, but we may have different results from different p values. So how do you guys think? If we have these choices, which I should choose? Or it depends?
Probably p equals 16, but it also depends on what you're trying to show.
Mm-hmm. What?
P equals 16. That's the more accurate one.
That is more accurate?
Based on what we were looking at earlier, yeah.
Based on what?
Based on what the graphs you were showing us earlier. That seems to be the more accurate one.
This one?
Yes.
But basically, we do not know like the true concentration here. So we cannot compare the accuracy. Like we only have the data. We don't know what's the true concentration at the unsampled location. So, but I think that's a good try. So for me, I would say it depends on the situation. For example, we are interested in PM 2.5 concentration in this area. And this area, like we are going to evaluate the effect to the people here, like especially for the kids. So in this case, like if I want to know the concentration here, I may choose the one that creates the worst scenario. So the one that gives the greatest concentration here, I will use that because I want to protect the human beings. So I will choose the worst scenario. Does this make sense? Yeah, so it depends on the purpose. And so for this one, do you guys have any questions? No? Yes?
So why is p equals 2 like the common number for it?
Yeah, that's a good question. I don't know.
That's one.
Yeah, but but I think usually we will have the square because like for the variance we also use the square, and the variance is the common, like the standard, like for the lost function or something like that. Yeah, yeah, I can do some studies on why they choose 2. That's a good question. So for this method, it also has some advantages and disadvantages. So it can estimate, it can estimate extreme changes, and it can, if we have dense and evenly spaced points, and then it will provide very good results. And it can increase or decrease amount of sample points to increase the cell values. For example, if this map is very large, so sometimes we are interested in this, we can just select the ones that is near it, because the weights of this far away, they are equal, like they approach to 0. So it can decrease the intensity of computation. It also has some disadvantages, like it cannot estimate above maximum or below minimum values because it is the weighted average of other points. Also, it is not very good for peaks or mountain areas. And again, because for these areas, we may have some extreme change, so it cannot do that job. And finally, I'm going to talk about kriging. So kriging is a geostatistical interpolation technique that considered both distance and degrees of variance. So in other words, kriging, because it is a statistical method, it can provide information about uncertainty, which is important to environmental science. And again, for kriging, the value that is going to be estimated can be expressed as the weighted average of the data from other sites times the weight. And we can also rewrite this into this form, and the lambda here refers to the weight. And in kriging, the weight is a particular function of distance known as variogram model, as we discussed before. So basically, if we know this lambda, we can do the estimation. But for lambda, we define the sum of different lambdas is equals to 1, because we want to have a unbiased estimation. And we also know that this is the variogram model that we already have based on our data. And in this case, we can also express the variance of our estimated value. And the variance can be expressed in this formula. So how to find lambda? We want to find the lambda I. So this is a bunch of values that minimize the variance of estimated value. So actually, we are doing the optimization. So basically, to calculate this lambda, we may need some other mathematical techniques. But the general idea is to find the lambda that can optimize this equation. So again, we have different, because we have different variogram model to choose. And here shows an example. Like we have high range variogram model, and we have the low range variogram model. So in this study, they just choose two different models. We can see we have different interpolation results. For the high range variogram model, we can see the shape is relatively large. But for low range variogram model, the shape is relatively small. So again, we may need to make the decision to choose which variogram model we are going to use. And here, this is the same data, and this is interpolated by kriging. And this is a variogram. And kriging also have some advantages, like it can provide the error and uncertainties of estimated surface. But the disadvantages is also very obvious. It is computationally very intensive. And so about this, do you guys have questions? Yes?
What's that c-value in that equation, the last one?
C-value?
The z-value?
Oh. The z-value refers to, like, we can consider the concentration at place of x0.
It's like the y value?
Yeah.
Okay.
Yes. So I use z-value. Oh, I didn't have explanation here. So to be more specific, z-value refers to the realization at place x. And this realization can be the concentration, temperature, or any other parameters. And any more questions? No? Okay, I think that's it. So you guys can take a look at this in the later. But here I want to emphasize one point. If r equals to 0, which means correlation coefficient equals to 0 of xy, we can say that they are uncorrelated. And here I want to show we cannot say they are independent. So uncorrelation and independence, they are different things. Here is an example. For x and y, we can calculate the correlation coefficient. The correlation coefficient equals to 0. But obviously, x and y, they are not independent. Like y equals to I think the absolute value of x. So as in our daily life, we just use them maybe interchangeably, but in science or mathematics, they are not the same thing. Yeah, and here are some just notifications. For the next week, we are going to do the meet with professionals, and it will be online only because the guests cannot physically attend here. And it will be on Tuesday and Thursday. So during the whole next week, we are going to have like the discussion with the like the graduated students. And here, each student will prepare 2 questions for each video and post on the discussion before Tuesday class. So during the lecture, we can summarize and ask these questions with them. And that's it.